In this section of the book, we'd like to look at surface area, and specifically surface area of surfaces of revolution, kind of the outside of a solid of revolution, the kinds of things we talked about in the volume section, the last section of the book. This does require you to remember the material on arc length, so the material on how you measure length along a curved curve. I will briefly recall it, but you have to have arc length to do surface areas. And you may recall that arc length integrals tend to be very, very difficult. And we picked some very special ones that we could actually calculate when we did that section. But I said that, if you had a more general integral, it would be impossible or so difficult that you'd approximate it using something like Simpson's rule. That's going to be equally true for surface area integrals, and so a lot of people just skip surface area when they do calculus altogether because the integrals are just too painful. But the idea is interesting, and I do want to do at least 4 examples, and so this should be pretty short, but hopefully kind of interesting. So what's the general situation? We're going to have some curve, well, maybe I shouldn't draw it that weird. I won't be able to draw what it looks like rotated. But you have some part of a curve in a plane, and we rotate that. We generate a surface of revolution, so maybe I'll rotate it around the y-axis. And you look at the surface that gets swept out as you rotate that around the y-axis. Or we could have rotated around the x-axis. But the point is, you take this curved curve, possibly curved, it could be a straight line, but typically it would be something that curves. You take this curve and you rotate it around some axis, and it generates a surface where I am not talking about the top or bottom being filled in, just the sides of this surface. And the question is, what's the surface area? How do you find surface area? So we want, what is the surface area? Or you could just say area of a surface of revolution. Well, of course, it's going to involve an integral. And so you chop things up into little pieces. And so what you do is you think of chopping this curve up into little pieces. And then between, on each little piece, you think of that rotated surface gives you, well, what's essentially a cylinder. Now it's slanted a little bit, but if you take this to be even smaller, the slant isn't so pronounced. And we know the area of a cylinder. So if I call this length right here, well, most people think height of a cylinder, I'll call it h. And then there's the radius of the cylinder, which I'll call r, for the radius. You probably know that the area of a cylinder is, well, it's its circumference times its height. Circumference of a circle of radius r, 2 pi r, and then times the height. So you get 2 pi RH. All right, but this h for us is supposed to be an infinitesimal little chunk of the length of the curve. And so what we have isn't h. We'll have a ds. I remind you that we used s for arc length on a curve. And so here we'll have an infinitesimal chunk of area. So the area of this infinitesimal cylinder, dA, is 2 pi r, and the r depends on, well, where you're rotating, the axis about which you're rotating and what the curve is. So I'm just going to leave it as r in our formula. But you get this, and then you have to recall how you calculate ds. There are different ways. So recall that ds, so here's a little infinitesimal change in arc length. There were kind of, well, it depends on how you count, but basically 3 different ways of looking at little pieces of arc length of a plane curve, so of a curve in the plane. One was if you had the curve parametrized by x equals x of t, y equals y of t, or if you prefer vectors, the position vector p of t is x of t, y of t. If you had the curve parameterized like this, then ds was the square root of, you take dx dt squared plus dy dt squared, and then multiplied times dt. On the other hand, one particularly nice way of getting a parameterization, or one common way of getting a parameterization, is your curve is described to you as the graph of some function y equals f of x. And then you should recall that, how did we get a parameterization of such a curve? Oh, we let x just be t, and then if x is t, then y is f of t. And if x is t and y is f of t, well, then I'll just, in this formula with the t's in it, I can replace every t by just x. And so in this setting, what you would get is, if t is just x, this is 1 squared. Wait, I'll do it in my head. Still 1. But you get ds equals the square root of 1 plus dy dt is dy dx. So dy dx squared. And then dt is dx. And so you have this. On the other hand, if you're given x as a function of y, then we had one last form. If you're given x as a function of y, then just by switching all the x's and y's, what you get is little pieces of arc length are given by the square root of 1 plus dx dy squared times dy. So how do you calculate surface area? You have a curve described to you, first of all, because we're talking about surface area of a surface of revolution. You have a curve described to you either parametrically, or as the graph of some function of x, or as the graph of some function of y. You use one of these formulas for infinitesimal pieces of arc length, and then dA, an infinitesimal chunk of area of the surface of revolution, is 2 pi times this radius, which you have to write in terms of either t, if you've got it parameterized, or x, if you're given y as a function of x, or in terms of y, if you're given x as a function of y. So how you need to write r in terms of whatever variable you've got in your expression for ds. But then in the end, of course, to get the total area, so the surface area, the area of the surface, you integrate as your variable. So I'll pretend it's t right now, since that's the general case, and you can let t be a or b, t be x or y in other cases. You just integrate from some initial t value to some final t value, the values that describe the piece of the curve you're talking about. So over here, that's what you get. Some integral as t goes from a to b. And that's what you do. That's it. How difficult is this? Well, it depends. If you don't pick some very special curves and axes, the integrals are terrible. but I'll pick some very special ones. So let's do one that you already know, just to see that things are working correctly. Or you may not know this. A lot of people know it. A lot of people learn it in high school geometry, but it's probably not proved to in any way. It's probably just, you're probably just given this as a fact. Let's find the surface area of a sphere of radius r. So how do you get a sphere as the surface of revolution? Well, I'm just going to revolve this part of a curve. So I'm going to take, let's call this x, call this y. I'm going to take this part of a circle of radius r, and I'm going to revolve that around the y-axis to get a hemisphere, and then we'll just we'll calculate that area, and then we'll double it. Yeah, we could do the whole sphere at once by revolving half a circle instead of a quarter of a circle, but there's no real point in doing that. So I'm going to calculate the surface area of the sphere by rotating this part of a circle around the y-axis. This part of a circle, so that quarter of a circle, I'm going to parameterize it. Now hopefully you know the nicest, there is no the nicest, but the most common parameterization of a circle of radius r. It is that the x-coordinate is r times the cosine of t, and the y-coordinate is r times the sine of t. I remind you quickly that cosine is defined to be the x-coordinate, cosine of theta at an angle of theta with the positive x-axis is by definition the x-coordinate on the circle of radius 1, and sine of theta is by definition the y-coordinate at an angle of theta with the positive x-axis. So on the circle of radius 1, we just get x as cosine and y as sine. So this is, but then when you scale out to a circle of radius r, you have these. You have to multiply by r. So this is the standard parameterization of a circle of radius r, centered at the origin, but we need to restrict our t values so that we just get this quarter of a circle. So that would be this, think of t as the angle with the positive x-axis. This is t equals 0, and as you go to here, that's t equals pi over 2. So we're going to have t between 0 and pi over 2. Okay. And we want to calculate the area of the surface of revolution that we get. So what does that mean? So that means that we're going to take the area, we're going to integrate as t goes from 0 to pi over 2 to pi. So think the area of an infinitesimal little cylinder, 2 pi r h, but h is ds, where ds is our expression for the arc length, a little chunk of arc length. So in terms of, I'm going to do everything in terms of t. So we need to calculate ds in terms of t. ds is the square root of dx dt squared plus dy dt squared times dt. This is the square root of dx dt is r times negative sine of t. So I'm going to write negative r sine of t squared. And then we get plus dy dt, so that's r cosine of t squared. So r cosine of t squared. So that's ds. You might think, well, that's not very nice. It doesn't look like we're going to be able to integrate this easily. Well, it is very nice, and you may have already seen what's going to happen. This is, okay, this is, if you square this, It wipes out the minus sign, and you get r squared sine squared. If you square this, you get r squared cosine squared. Now you should see a sine squared plus a cosine squared, which you know is 1, but what about the r's? Oh, well, there's an r squared both places. You can factor out the r squared. So this is r squared times sine squared plus cosine squared. But that's 1. So this is the square root of r squared, which is really the absolute value of r, but r is a radius, so it's already greater than or equal to 0. So this just all collapses to the very easy, this equals just r dt. So this is extremely nice. ds is r, a constant, times dt. That's what we've just arrived at. The ds equals r dt. That makes this integral very, very nice. So what we get for the area is the integral as t goes from 0 to pi over 2 of 2 pi. I'm going to leave a space for what we put in for this little r, ds, which is r dt. We still need the radius in terms of t. What radius? Capital R? No. The radius, remember you're thinking of little chunks of the curve, and the radius in that formula is the distance from the axis that you're rotating around to each little piece of the curve. So the question is, in terms of t, what is this radius at each t value? Like you have one t value down here, another t value. So our r as a function of t is clearly changing as t changes. As t moves, we move along here, but each time we want the distance from the point on the curve to the y-axis. But that distance, the distance from point on the curve to the y-axis, is the x-coordinate of the point. The x-coordinate of the point in terms of t is capital R cosine of t. Right? This distance, this radius of our rotation at each point is just the x-coordinate on this curve. But in terms of t, that's r cosine of t. So here we get an r cosine of t. Now, 2 pi and r squared, those are r times r, those are all constants. And so we pull out a 2 pi r squared. We need to integrate cosine of t with respect to t, an antiderivative of cosine of t, sine of t. And you evaluate from 0 to pi over 2. So you plug in pi over 2. Sine of pi over 2 is 1. You subtract what you get at 0, which is 0. So we just get 1 times 2 pi r squared. So our integral gives us the area of this surface of revolution. We get that it's 2 pi r squared. So the area of the whole sphere is 4 pi r squared, as you should know. So what we just found. The surface area of a sphere of radius r is 4 pi r squared, which you may have learned in high school. Okay, all right, let's calculate an area of something that we don't know a formula for ahead of time. So another example. Let's take y equals x squared, so your most basic parabola, but only the part in the first quadrant. And let's go from 0 to 2. So we'll take this part of the curve. And rotate that around the y-axis, generating some kind of cup looking thing, although it would be a pretty bad cup because it wouldn't rest. You couldn't ever set it down. You'd have to have some weird cup holder. And we'd like the surface area of this, maybe it's a chalice, maybe it's got a base on it. Anyway, we'd like the surface area of this, regardless of what we're thinking of it as. Okay, you're given y as a function of x. It's true we could parameterize, but the parameterization we'd pick would probably just be the obvious one, x equals t, y equals t squared. But we don't need to do that. We know that if we do that, what we get is the formula for a little piece of arc length, in this case, is this. And so it's 1 plus 2x quantity squared dx. So it's the square root of 1 plus 4x squared dx. Okay, that's ds, a little piece of arc length of this curve that we're rotating to generate the surface of revolution. So what's the area of the surface of revolution? Well, it's going to be the integral as x goes from 0 to 2. Don't get confused. You do not come over here and start at minus 2. We go from 0 to 2 to get each piece of the curve that we're rotating. The whole 2 pi r ds calculates the area of a whole infinitesimal cylinder, including what you've rotated around here. So you're taking care of this part over here. Don't be confused and start integrating at minus 2. You just want to take yourself over each piece of the curve and then see what area that gives you as it sweeps around. So the integral is as x goes from 0 to 2, 2 pi r, and then ds. But we're writing ds like this. And so this is what we'd like to calculate, except it ought to bother you. There are two variables. Pi is a constant, but here's an r and here's x. We're integrating with respect to x, and so we need everything in terms of x. And so once again, as in the previous problem, we need to know, as a function of x, what is this radius, the distance from little chunks on the curve to the axis of rotation, revolution. And the answer is, once again, it's the x-coordinate on this curve. So what's the x-coordinate on the curve in terms of x? It's x. And so this r, in this case, is just x. Just like it was before, it was the x-coordinate on the curve. It's just before, in the last problem, we had the curve parameterized. So yeah, it was x, but then in terms of t, x was r cosine of t. But here we're doing everything in terms of x. It's just the x-coordinate. It's just x. And so this is the integral that we need to calculate. Now, this may look bad, but it shouldn't look so bad. If you remember techniques of anti-differentiation, you want to make a substitution. Let u be 1 plus 4x squared. And then you should kind of be able to do this first part in your head. If u is 1, is this going to work? If u is 1 plus 4x squared, we'll have the square root of u. But what's du? Well, du would be the derivative of this, so that would be 8x dx. But we've got an x dx, and you can always fix the multiplying by a constant. So that substitution will work. We will be able to anti-differentiate this, so use the fundamental theorem to calculate this integral. So let's do it. So the area that we're after is the integral from 0 to 2 of 2 pi x times, I'll write the square root as raised to the half power. That's how we'll want it for anti-differentiation dx. And I'm going to make the substitution u equals 1 plus 4x squared. That means du is the derivative of this times dx, so it is 8x dx. So if you want, you could just divide by 8 although really we could divide by 4 and absorb the 2, but it doesn't matter. We get 1/8 du is x dx, and this integral becomes, all right, we have to calculate our new limits of integration, 2 pi. Part of the point of the substitution is that the x times dx, that part, whether you rewrite it with the x over there or not, x times dx is 1/8 of du. And then this, 1 plus 4x squared is just u, so we get a u to the 1/2. And then the x dx is 1/8 du. And since it's a definite integral and we've made a substitution, the nice thing to do is to change your limits of integration to describe what your new variable does. When x is 0, u is 1 plus 4 times 0 squared, so u is 1. And when x is 2, u is 1 plus 4 times 2 squared, so 2 squared is 4, 17, u is 17. Okay, so you get this, the 2 pi divided by 8, that's pi over 4. That's a constant. And then we have to, so we've got the pi over 4. Then we integrate u to the 1, anti-differentiate u to the 1/2. It's the power rule. You add 1 to the exponent, divide by the new exponent, and evaluate as u goes from 1 to 17. If you invert this and multiply, you get a pi over 6. Pi over 6, so I've taken care of the 2/3. I invert it and multiplied. And then I'll get 17 to the 3/2. What's 17 to the 3/2? It's 17 to the 3/2. You can get out a calculator and figure out what it is, but I'm going to leave it as 17 to the 3/2. Minus 1 to the 3/2. All right, that one I'll do in my head. 1 to 3/2, 1. And that's the answer. That's the surface area. Roughly, if you're just trying to do an approximation in your head, 17 is approximately 16. Then 3/2 would be take the square root and cube it. So roughly, you take the square root of 16, that's 4, cube 4, so that's 64. You get 63. Think, oh, divided by 6, it's roughly 10. Pi is about 3. So order of magnitude, this is about 30. Now, that's a very, very rough approximation. But every now and then it's nice to do those in your head so that you know your answer isn't ridiculously off. Like if you did this on a calculator and got it to 2 million, you should suspect that you punched something wrong on your calculator. All right, let's do another example. Y equals x squared worked out nicely with the substitution. What about y equals x cubed? Well, y equals x cubed works well if you rotate about, is reasonable to do if you rotate about the x-axis, but not the y-axis. So let's look at this. So here's y equals x cubed. And I just want to take the part. Again, I'll go between 0 and 2. My scale is going to be wildly off. Okay, and I want to rotate this around the x-axis instead of the y-axis and get this weird curvy cone thing. And we'd like to calculate its surface area. Understand, though, I am not talking about, when I say surface area, I'm not talking about with, so we're rotating this, and we're looking at the area it sweeps out. So that doesn't include this circle, or this disk at the bottom. It's just the sides. Okay, so we'd like to find the area of that. All right, so the surface area. Well, we're going to once again integrate as x goes from 0 to 2. We're going to have 2 pi r. And we want ds, a little piece of arc length. But again, we're given y in terms of x, so we'll use the square root of 1 plus dy dx squared times dx. We need to write the radius in terms of x. Now you get something different. In our last two problems, we were rotating around the y-axis, and so the distance between the axis of revolution, rotation, revolution, I shouldn't confuse those, but I might have. The distance between the axis of revolution and the curve was just the x-coordinate on the curve. But now we're revolving around the x-axis, and the distance from the x-axis to the curve, so this radius that appears in the integral, is the y-coordinate on the curve. But we need it in terms of x, so the y-coordinate on the curve in terms of x is x cubed. And so the integral we have to do this time is the integral from 0 to 2 of 2 pi r is x cubed times the square root of 1 plus dy dx is 3x squared, so 3x squared dx. Before I do this, I should say, there's something I should say. Once again, we're going to make a substitution for what's under the square root sign. This will be 1 plus 9x to the fourth. And then if you let u be that, then because it's 9x to the fourth, if you let that be u, then you'll get a 36 x cubed dx, and you have an x cubed dx. So that substitution will be very nice. Had we rotated this around the x-axis, around the y-axis. Had we rotated this around the y-axis, our radius would just be x. Right? In terms of x, it would just be x. And then we'd have an x there, and we'd have a 1 plus 9. It wouldn't change this. We'd have a 1 plus 9x to the fourth here. And then the substitution u equals 1 plus 9x to the fourth doesn't help much. It's a much more difficult problem. So understand that different curves about different axes or different axes of revolution can give you wildly different integrals to do, and certainly should give you different surface areas. All right, but let's do this one. So we get the surface area, in this case, is the integral from 0 to 2 of 2 pi x cubed times the square root of 1 plus 9x to the fourth dx. We make the substitution u equals 1 plus 9x to the fourth. So du is 36 x cubed dx. I'll divide by 36, so we get 1/36 du is x cubed dx. And so this integral becomes, in terms of u, we get a 2 pi, the square root of 1 plus 9x to the fourth. That's now just the square root of u, so I'll write that as u to the 1/2. And then the x cubed and the dx together give us 1/36 du. We should change our limits of integration. When x is 0, u is 1, right? When x is 0, u is 1 plus 9 times 0, so u is 1. When x is 2, this is 16 times 9, that's 144, so we get 145. Okay, so, all right. So we get this. What is this? This is pi over 18. Right? That's 2 pi over 36, pi over 18. Again, we're integrating u to the 1/2. You add 1 to the exponent, divide by the new exponent, and you evaluate as u goes from 1 to 145. Okay. So what do you get? You invert this and you multiply. So if you invert this, you get and multiply, you get pi over 27. Pi over 27, and then you get times 145 to the 3/2. And then minus what you get at 1, which is again 1. So this is what we get for the surface area. Again, 145 is approximately 144. So its square root would be 12, and then you get 12 cubed minus 1. Okay, I'm not going to approximate this one. But anyway, this is what you get for the surface area. All right. I only want to do one last example. In this example, I want to look at the volume of a solid of revolution and the corresponding surface area of the surface. This example is frequently known as Gabriels Horn. It looks kind of like a long trumpet, which is frequently how the archangel Gabriel is depicted in religious paintings. But it doesn't matter whether you call it Gabriel's Horn or not, except that if you're trying to find it in the index of a book, that's where you'll usually find it. Or if you're Googling it, this is what you want to Google. Of course, you might also want to Google surface area at the same time. So what is it? Suppose you take the curve y equals 1 over x. And here's 1, 1. And we're going to take this infinite part of the curve that gets closer and closer to the x-axis, and we're going to rotate that around the x-axis. So it looks kind of like a long trumpet or horn thing, with this being the big open end, and if it weren't infinitely far away, the mouthpiece would be down there. And what we'd like to do is calculate the volume of the solid of revolution. So you take this entire area under the curve and above the x-axis, and you rotate that around, so you calculate the volume of the solid of revolution. And we'd also like to calculate the surface area of the surface of revolution. Again, that doesn't mean you include this part over here. All right. So we just did volumes of surfaces of revolution in the last section. Hopefully you remember. We'll do this by disks. Volume of this solid of revolution. Each cross section of Gabriel's horn perpendicular to the x-axis is just a disk. It's just a disk. And its radius is just the y-coordinate on the curve. So remember, to get the volume, you would take the cross-sectional area, that's the area of inside a circle of radius r. So that's pi times the radius squared times, then you thicken it up a little bit in the direction of along your axis, so times a dx. And now x will go from 1 to infinity. But r here, just both for surface area and for calculating volumes, is the distance between points on the curve and your axis of rotation. It's the y-coordinate on the curve, so it's 1 over x. So we get this. Of course, this is an improper integral. One of its limits of integration is infinite. We have to take a limit as we approach infinity to define the volume, but that's fine. So we do that. So the volume, I'll put in the limit now. It's the limit as b approaches infinity of the integral from 1 to b of pi times x to the minus 2 dx. Pi is a constant. You pull it out. To integrate x to the minus 2, use the power rule. You add 1 to the exponent, divide by the new exponent, and evaluate as x goes from 1 to b, and I left off the limit. Okay, we need the limit of this. So what do you get? You get this is the limit as b approaches infinity of pi, and then there's a b to the minus 1, so 1 over b, but negative that. So we get a minus pi over b, and then minus what you get at 1, so we get minus minus, so we get a plus pi. This. As b goes to infinity, this denominator goes to infinity, so pi divided by that goes to 0, and we're left with pi. So the volume of this infinite solid of revolution is just pi cubic units. Yes, it is kind of weird how often pi comes up. On the other hand, we are doing solids of revolution, so you kind of have cross sections that are circles, so it's hard, or inside disk, so it's hardly surprising that pi comes up again. What's really interesting, well, of course, it's in the integral to start with. What's really interesting now is to calculate the surface area. Strangely, we can calculate it without actually finding an antiderivative, and that's because we'll just show that it's infinite. The surface area will still have x go. To calculate the surface area, you still have x go from 1 to infinity, and then it's 2 pi times the radius. The radius hasn't changed. It's still the y-coordinate on the curve. It's 1 over x. 2 pi times the radius times a little chunk, times ds, a little chunk of arc length, which would be 1 plus, since we're given y in terms of x, 1 plus dy dx squared. So this is 2 pi times the integral from 1 to infinity of 1 over x times the square root of 1 plus dy dx. This is x to the minus 1, so dy dx is minus x to the minus 2, or if it looks better, minus 1 over x squared. So when you square this, you get 1 over x to the 4th. And this is the integral that we'd like to calculate. But as I said, what we're really going to see is that it's infinite. So why is that? Okay, let's see. So we need to take the limit as b, so this is the surface area. The limit as b approaches infinity of 2 pi times the integral from 1 to b of 1 over x times the square root of 1 plus x to the 4th dx. But if you remember, integration is monotonic, which means if you integrate something bigger and you go from 1 to a bigger number, so you go from a smaller a to a smaller value to a larger value, then bigger functions, functions that are greater than or equal to other functions, give you integrals that are greater than or equal to the other integral. And what I want to say is 1 plus x to the 4th is certainly greater than or equal to just 1. In other words, for each b, this part, this is greater than or equal to the integral from 1 to b of 1 over x times just the square root of 1 dx. Because because this 1 plus 1 over x to the fourth is greater than 1. So, but this one, this integral we could do. This integral, finding an antiderivative, we can't do. But this is just the natural log of x. We could put in absolute values, but our x values are positive, from 1 to b. So this is the natural log of b minus the natural log of 1. It's just the natural log of b. And so what we get is that this quantity that we're taking the limit of as b goes to infinity is greater than or equal to, is greater than or equal to 2 pi times the natural log of b. But as b goes to infinity, the natural log of b goes to infinity. And so this thing that's greater than that has no choice. Greater than or equal to that, this limit has to be infinite. And so what we find is that this limit is infinite. So this is the fun part of Gabriels Horn. It is this solid of revolution that has finite volume. Its volume is just pi. And its surface area is infinite. And so what people say is something like, yeah, that means you can fill it up, but you can't paint it. And then if you're thinking along the right lines, you say, yeah, but what if I filled it up with paint? Wouldn't that paint it? Right? Painting it kind of refers to the surface area, and filling it up refers to the volume. Is this a paradox? No, it's not. You need to think about it, but let me try this analog, and hopefully this will help you think about Gabriels Horn. Take a 1 by 1 by 1, whatever unit, 1 foot by 1 foot by 1 foot cube. It has volume 1 foot, 1 cubic foot. I don't know why I said 1 foot, 1 cubic foot. So everything's in feet, cubic feet, and square feet, and then I'll just talk about numbers without units. So it has volume 1. What's its surface area? Well, each side is 1 by 1, so 1 square foot per side, and there's 6 sides, so its surface area is 6 square feet. But we're going to drop the units. We know we're in square feet and cubic feet. So its volume is 1, and its surface area is 6. Chop it in half. Just take the cube. Take the cube and chop it in half. And separate the two halves. Separate the two halves. You didn't change the volume. Right? If you do that, you don't change the volume. The volume of the two halves separated, still 1 cubic foot. But you have increased the surface area. You have all the surface area you had before, and you've exposed 2 more faces. So your surface area just went from 6 to 8. From 6 square feet to 8 square feet. But you can keep doing that. Each time, take one of the two halves and cut that piece in half. And then do it again. What happens is your total volume never changes, and your surface area gets arbitrarily large. Right? You can make, by chopping enough times, you can make your total surface area bigger than anything anybody names. So what you should think of is continuing this process indefinitely so that you end up with something, continue it to infinity. You end up with a volume of 1, but an infinite amount of surface area. What does this have to do with filling it up with paint, but you can't paint it? Right. If you had started kind of somehow with a cube full of paint and somehow sealed off the cubes as you were doing these cuts, always sealed, put some shrink wrap on each side or something, seal off the paint. What happens is that on some of your piece, as you keep chopping this piece into thinner and thinner rectangular solids, yeah, filling it up with paint paints the surface, but with a thinner and thinner amount of paint, so that you could do. You can't paint the surface with something of uniform thickness, because then you would take the area times that uniform thickness and get kind of the volume. But if you make the amount of paint you're putting, the thickness of the paint you're putting on the surface smaller and smaller as you cut it and expose more surface area, then yeah, you could paint it. It's just that the layer of paint has to get arbitrarily thin. Of course, you can't do this in practice. You can only cut things so many times. At some point, you'd be splitting atoms, your paint would blow up, you'd blow up, the whole process would stop. Anyway, it's an interesting theoretical, Gabriels Horn is an interesting theoretical thing to think about, but don't let it bother you too much. All right, next time we will do some more applications where the integrals are typically easier more manageable than surface area integrals.